That should take maybe, yeah, I think I can do this in 10 minutes. Does this sound good? And then we have like still sort of 45 minutes for the code thing. Okay, let's do that. All right, so proofs. Okay. First of all, like there were like a couple of formats, and they have all these acronyms, and I want to explain them a little bit, and maybe also a little bit the history. So very fast. There were, of course, resolution proofs. This was, I think, in the SAT competition 2009 by Van Gelder. So nowadays, um, nobody does them anymore. So like they're like two sort of new versions. I would say like LRAT or trace check. So we'll see it on the next slide. And then because of that, people came up with this RUP, which is actually already in a paper by Goldberg and Novikov in 2003, and then Van Gelder in 2012, which means you saying kind of, in essence, dump the learned clauses. Also, Minisat version had this once, but it's like clearly first there in this Berkman context. The real breakthrough for all of that, however, was when Marijn added this D. I don't know whether you see the D is bold here. Okay. So the RUP is this format here by Van Gelder, which just sort of dumps learned clauses. And the D is, this is very cool. Marijn had this idea that, well, why is checking proof so much slower? Well, because the checker has all the clauses, while the SATSO, of course, throws away all the clauses all the time. So we discussed this just before, right? So this reduce is very important. And with this glucose style LBD based reduction, you really throw, I don't think like you throw away like 95% of the clauses or even more in a real run. And the checker should actually know about that. Then it can be way faster. And that's why the idea was to put into the proof the time at which a certain clause previously learned is not used anymore. And that's now kind of the de facto standard in the SAT competition. Actually, we now move to this RUP replaced by RAT. And I have some slides on that, but this is exactly the part which I don't want to go into detail much. But these proofs were actually born out of our work on preprocessing, which, like in particular, our block clause paper and follow-up thing, which I have to admit are not as important and successful for speeding up SAT solving, but they were really extractive to come up with proofs, and which is a kind of a contradiction, because like in when we use these sort of like notions of redundancy, you want to remove clauses, while in proofs you want to add sort of clauses, and at the end, of course, the empty clause. But anyhow, so there were like some big proofs done this way. The first very big one was the one by Marijn. There was actually something before on Erdős. I forgot to put that here, but they didn't use the thread proof system. And then the largest one here is this sure number 5 with 2 petabytes. What's even more interesting, I think this is why this is so important, is we now have certified proof checkers for this proof. So this sure number 5 is really checked by sort of, I put it this way, so this is as correct as you can get it on this world, because we have like a higher order proof checker which has a trusted kernel. And that's probably more trusted than sort of proofs on paper, mathematical proofs on papers. And also, like the first one was in the Koch prover, but there's also one in ACL2 and Isabel. And actually, in the SAT competition, they're checking these proofs, I think this year for the first time, also with ACL2. So if a SAT solver in the competition claims a formula to be unsat, it spits out a thread proof, or mostly actually a true proof. And then this will be checked by well, it will first be trimmed by thread trim, then translated into LRAD, and then it will be checked by ACL2 to be really a proof. And then you can actually be really 100% sure that this is an unsat formula. Okay, here's an example, and that's I think what I want to do. So the Timex format, Then the thing I came up with is trace format, where you put the clause. So you see here the clause. These are original clauses because there's no nothing in between. This is the difference between original and learned clauses. Learned clauses here would put the antecedents. So this learned clause here would be the result of these two clauses, and you can have more than two antecedents, like here 1, 10, 2. And then this is kind of the learned clause, this 11 clause, where you see the number here, it's a unit -2, which is the result of one and this clause and the clause 2. And then the LRAD format is very similar to that one, which came later, but it has this deletion information in it, which I'll explain in a second. So the resolution trace is longer, of course, because here you can only have like two antecedents. Or like after the first 0, you always have two clauses. Like here's like clause 11, this one here, plus clause 4, like 2 and -1, and 1 are resolved, and you get like -2. Okay. And RUP clauses are the shortest ones. And here you only add the learned clauses and nothing else. So it's similar to this one, but you just add the clauses themselves, not how you sort of derive them. These are sometimes called hints, and you need these hints for fast checking, but it's like way larger, right? And in essence, this became the standard. However, for even faster checking, you would just learn sort of millions of these guys. And this slows down the checker dramatically. So that's why you also tell, you can tell the checker, okay, so after I derive this clause, I don't need these two clauses anymore. Okay, so delete them. So you kind of intersperse this proof with deletion information. And yeah, down here, you actually see how these proofs were generated. So they're really not like made up, but they're kind of generated from real tools. And that's kind of the input of the SAT competition. And then if you think about these 2 petabytes, they would look like this. Of course, there's a binary version of it, which gives you kind of a factor of 4 in size. And then you can zip it, which gives you sort of another factor 10. So like the byte-wise, the proofs are 40 times smaller than this ASCII representation. Okay, then what I said already, like we worked on in the Discord, I said this, we worked a lot on this sort of trying to simulate structural information. And oops, my screen wants to power off, just a second. Yeah, here's an example, and you can do work over this later. So you have some gate structure, and you encode this with state-in encoding. You get that one. Now you imply preprocessing, actually block clause elimination, and I explain it here. And then you get that one. And this is a couple of effects which you could describe on the structural level by removing sort of polarity clauses, or also like things which only occur tree-like. And of course, this seems to be, and it's also effective in the sense that it reduces the size, but it turns out that at least in the latest solver, you should actually switch it off. It's we could discuss why this is the case, but it's just an empirical fact. Maybe all the other preprocessing and techniques became so much optimized that like removing some clauses, maybe even like 50% or 30% of the clauses which are not really useful is not good, because you will also forget some which should be used. Okay, then we came up with this red, which, yes?
So about the monotone input removal?
Sorry? A monotone input removal, you have a, so it's like pure literal, but on circuits. You know, pure literal, right? Like in a CNF, a variable occurs only positive. Now, if you have a circuit and there's an input to this circuit, and this circuit to all the sort of probes where you look at it or at the outputs, only occurs sort of in an even number of negations, for instance, or even only in an odd number. So, of course, in one of the two cases, then you can fix this input to either true or false.
So this is just looking at the structure of the circuit.
Yes. However, you don't need that, because block clause element simulation would just do that for you without knowing about it. So it would just do this for free. So that also means, you see, through all these years, we came up now with methods which are much stronger than the structural methods. They can be implemented very fast. But at the end, they are actually nowadays, with the latest version of solvers, they're actually less useful. So you should not spend any time in implementing them on the structure because they're actually useless.
So an input could be monotone semantically, but I mean, it might be difficult to detect it, right?
Yeah, so on the circuit structure, the algorithm would just like compute parities, like occurrences of an input, right? And then propagate this. But then you also have these polarities downwards, right? So like the Playstick-Greenbaum a bit where you sort of, you check how often does a gate occur in the output positively or negatively, and then you don't need like all the SAT clauses, and all of that is very pretty complicated, in particular if you have a DAG, right? So here we don't have a DAG because there might be mixtures and you have like multiple parents. And so I know what I'm talking about. So I had a bug in the original BMCs actually, and this was used in IBM. And they had a counterexample of length 83, but my tool said 82 is also possible. And this was actually then finally root caused it to a bug where I mixed up and dropped one clause, which should not have been the case in the encoding. And then afterwards, of course, like if you have this block clause elimination, you don't need to worry at all at this complicated algorithm, but you just implement block clauses and you would get the same effect, way more actually. But then at the end, this is the other story to it. Nowadays, like not 10 years ago, but nowadays, block clause elimination is switched off in Cadigo, and I haven't even bothered to implement it in KISAT because it's slightly slowing down the solver. So it gives slightly less soft instances.
Thanks.
Then there's this rat, and this takes a time to swallow. So already the block clause definition here, when I looked at it first, Oliver Kuhlmann came up with this. Marijn explained this to me, and then Matti and I worked on this. I like one day I understood it, next day I didn't believe it. Now the rat is of course sort of the follow up on that. That's getting more complicated. Oops. But all of that led actually to a nice journal which summarizes it. It's a journal from 2000. It doesn't say here, so it's a journal from 2015. But we got an award at this one of the biggest AI conferences because of the sort of one of the most influential papers in the last 5 years in that journal. But as I just explained, this is also for QBF, by the way. At least for SAT, it seems these clause elimination techniques are less useful, even though they allowed all the theory on proofs, right? So it's like it sort of um, in this procedure of coming up with new proof systems, it was extremely important. For QBF, they actually give a benefit, but for SAT, they hardly give. Okay, and then recently, Benjamin, I can circle him, finished his PhD thesis, and this is now the next step. I will not explain because this is even more sort of dense. But his first result was this set block clauses and super block clauses, and this is an extension of block clauses. And then we came up with this theorem, which I put in large font here, which is when we came up with this one at the whiteboard here in the office, and we just met, Marijn was also here, and then we came up with this theorem, and we said now we're not going to need to write any theory anymore about redundancy in CNF, but of course not true. But back then we thought, and that's this theorem, which I also don't have time to explain. The only thing I want to point out here, it requires here this omega, which is a satisfying assignment of a different formula. And this leads then to sort of a weaker version. So this is really sort of a semantic version, which we call propagation redundant. So the difference here between these two here is like semantic implication. Well, here you just use unit propagation, like something polynomial. And that got lots of best papers. So Benjamin, I think, got like 5 best papers for each PhD thesis. And it was also recently it was used by the picked up by the proof complexity like community. So Sembas and Neil Tappen had a nice SAT+SMT paper, and well, and then my student and I actually published that this PR thing is actually not as powerful as we thought, because one other very old like clause redundancy property, cover clauses, was not covered by it. Okay, but I want to show you a little bit, like, because I think this is nice. This was done by Marijn for NASA formal methods, which shows a little bit how these proof systems work. So this gives you an intuition why these clause redundancies are important. So I guess you know this problem. It's called mutilated chessboard. So you see here chessboard on the left, and here, and 2 corners are gone. Okay, and if you look carefully, these have the same color. And then it's a classical questions: can I sort of cover this chessboard with dominoes in such a way that no domino sticks out? And the answer is no, right? Because the sort of the mathematics, this is what you give to kids to think about sort of inductive proofs. Well, it would be because, like, if you think about you have the property that every domino covers a black and a white field, right? Like, and therefore, no matter how you try to cover, uh, um, you can the number of black and white fields covered is the same. However, we have like two the corners here of the same color removed, and therefore we cannot we will like a covering which would cover all of them would violate this would not be able would violate this invariant. Okay, and now if you give this to us a SAT solver, the way you do it, you put, like, for every position, you put a variable and you say, is there a domino? And then you would say, is it like looking to the right, or is it looking to the downward? And then you put like lots of constraints, right? Like saying, like, of course, like if the domino here is at this position, then another domino cannot be here. So like an overlapping constraints. And that would then be sort of precisely characterize the problem whether this is possible. This problem was actually submitted to the 2018 competition by a Russian researcher. Like, it's called MChess if you want to check the competition. And I think nobody solved it. Actually, I think like Cadigal solved it for some reason. One smallest instance, but like 4 instances were in this. Now we have an automatic way, which we call SDCL, to find really high PR clauses, like these like high powerful redundant clauses. And we were running when we submitted the paper on SDCL to the HVC. If I go back 1 page, it's this HVC paper here. Okay, we knew that the reviewers would ask, did you also try this SDCL on competition benchmarks? Of course, we tried. And then the SDCL solver, which I implemented, is called Sadical. You can Google it if you want. Sadical. Could not solve a single instance from the competition, which is really bad, except for these MChess instances. And what happened is that SDCL found redundant clauses which are not model preserving, which are much stronger than the common learned clauses by an CDCL solver. So here on the right, you have a CDCL conflict. Here you have a conflict. And then that would be the learned clause after clause minimization, right? And clause analysis. And this, of course, this rules out a couple of, you see, all these kinds which are not covered are kind of don't cares in the search space. So this clause will also rule out any other covering which you would add here. But it's like pretty large still, right? While SDCL solver can learn here clauses which the following clauses, which means that if you have a covering which looks like, oh, sorry, I should keep the thing on, which has such a shape, okay, then you don't need to search for covering which has this shape, because these two are indistinguishable, right? So if I flip these two dominoes up, okay, around it, there will be exactly the same situation. So that's why I can add the clause which says if I have these two clauses already checked, I don't need to check these two clauses. Sorry, dominoes. And the same is true for these ternary dominoes, where you can sort of move this domino down here, okay? And then, of course, around it, it doesn't change. And our SDCL solver just magically found these redundant clauses. Now, what Marijn looked through the proof and then generalized it and figured, oh, you can add all of them, of course, also manually in general proof, which is proof checked. And this way get like exponential reduction. And this is the picture I want to skip. And here are the numbers. And here down here, yeah, almost no solver could solve this guy. Well, yeah, it's not true. Like 15 could be solved, but 70 not. And this was, of course, the 2018 version. And now this can be done very fast and even be checked with ACL2. All right, so this concludes the pre-processing, and I would go to code if there are no questions. Okay, no questions on the pre-processing. All right, so, okay, can you see that, right? I think you should see the terminal, otherwise somebody needs to shout.
No terminal.
No terminal?
Seeing a blank now.
Okay.
Now it works.
Now it works? Okay.
Yeah.
All right, so let's get, for instance, what one category. So I have this strange thing here. Just a second. I need to move it. Oh. Okay. So this is maybe those of you who have a machine can also do that. And then
We don't have it. We don't see the
you don't see it. What did you
anymore.
say?
It was we were seeing it, but not anymore.
Maybe I just share the window for now, then I cannot go back. Let's do that. Do you see it now?
Yes.
Yeah.
All right. So the standard way would just be to do configure and then make. And this is so fast because it's C++, because I use TC cache. But it's still much faster to compile. I don't want to elaborate. Anyhow, so what this thing generates, so this would be the typical sort of flow to do this. So you configure, you make test, and then what you see here are regression tests. So maybe we'll check out a couple of them. It's important for those of you who want to actually work on that solver. So so the first thing which will happen, it would run some sort of application tests, which are in a separate directory, like these are called usage, right? And then it would move on to regression tests. And as you can see, these regression tests are of a special form. So let's for instance have a look at this one here. This is actually an API trace. And so if you think about the API server format I showed you, this is exactly what the solver accepts. And for instance, if I would use Caticle on one of the test CNFs, for instance here, trying to factor this number. Okay, then it says, of course, unsat. And then I can dump a proof also. So this would be then a proof. Oh, this is binary, so I should not. I think it's called no binary. Then I get a no, it's called differently. So I forgot how it's done. Sorry, I'll do the proof with the on the command line. The window is in the way. Just a second. No, so I forgot how this is done. Sorry about that. So anyhow, so the proof is in a binary format, which I cannot show, but otherwise it would be you see it would be like this ASCII proof we had before, and that's just like clauses added and removed. Okay, so sorry about that. Anyhow, but what you could also do here is Cadico API trace is equal to trace, and then oh no, this was the wrong thing. Cadico. I forgot how it's called, of course. It's now we have it. See it? All right. So this is now the API trace we generated by parsing this Dimex file and then going to the API to the solver. And it looks exactly very similar to this regression test, right? So you see like here's a clause like with variable 94 added. And then, okay, so then we solve it, then we ask for the statistics and also for memory usage, and then we delete the clause, the solver, okay? Again, this thing in my way, it's difficult to do this. Yeah, right, so this was a regression test, and there's a tool which is called Mobicle in the build directory, and it would just, if you give it, it would just replay this trace, okay? You get the point. So what does replaying mean? Well, it parses this trace, and then of course would call the API functions which are needed. Okay, now let's go back to this situation where we, this one here, where we do a test, and then we have these regression tests, right, which are like often bugs. Then we do also have CNF tests, right? So just like instead of using the traces, the CNFs, and you do the regressions, of course, first because they would trigger bugs earlier. And then after this is done, I'll show it at the very end. Mobicle is actually called, and Mobicle is actually a model-based tester for Cadico and build. And if you would run it just like, oops, like that, it would just, the reason why it doesn't nicely is because the window is too big. It would just generate traces. The traces we just saw, they're kind of random. So if I stop it for a second, you will see here's like currently one trace with this random seed. It has 2,304 API calls, 55 variables, and 24 clauses. So if those for you who know this is kind of a grammar-based fuzzer, and the grammar is kind of hidden behind these guys. And this part is very important. This is the number of incremental solving calls. So now the SAT solver is called, solve is called 3 times. Think about again of our API SIR model where we moved from unknown to solve, and that's happening here 3 times. Okay, and because this is now the version on GitHub that has been roughly tested, there's no bug in it, so you won't see a bug. So I need to plant a bug now. But before I show you this, I want to show you how I usually do this on the cluster. So I have here on the cluster with 500 cores, I can run in an hour roughly, oops, this number of test cases. So 500 million, half a billion test cases in an hour with this setup, as you just saw. Yeah, you saw like this guy was already like doing 164, and if you do this in the class, it'll be 500. So anyhow, before I do a release, I would just run this thing on the cluster with say half a billion, or maybe even if I let it run for 10 hours, you see, then it's 5 billion test cases. Billion, not million. Okay, let's go back to the to this thing I wanted to show. Now we're going to plant a bug, and for instance, this is the minimization functions where we discussed also in the lecture, and maybe you see already one thing here. I try to put lots of comments into the code. So I claim at this point this is the most documented SAT solver. And if somebody of you, for instance, wants to learn about SAT solving, maybe going through these comments, and there are also references to papers, is really best. And in addition, if then at one point you don't understand something, even though there's like links and documentation, please let me know, and I will put it in here. For instance, here are two things which one is actually related to a paper, so which is a poison idea from Alan van Gelder. But another one, this is just a solution to an exercise in Donald Knuth's book. And this poison here, for instance, this is of course described in the paper here. This is Donald Knuth's idea, so maybe let me try to explain this. Okay, when you do the recursive minimization of a learned clause, right? Then you're actually you might need to do that first search on this implication graph, right? And this L here, this is kind of the decision level. This is all the information for this particular decision level. And now if you add this decision level there, during the conflict analysis, we only saw actually one literal, okay, of that decision level. Then it's not possible that minimization would actually remove the one we just trying to remove, this one here. Right, because there should be then another one on this decision level, because you cannot remove that one without having another one already sort of in the clause which you want to remove. And the reason for that is because the minimization means that as soon as you kind of go to a decision level where you want to remove a literal, then this decision level will not go away, right? Because we always propagate on a decision level until conclusion. And therefore, if you count how often have you seen during conflict analysis that level, and this count is less than 2, well, then just give up. It won't be possible to do this. Okay, so now, for instance, we can make a typo. Okay, so we say, oh yeah, then we can remove it. And that's of course wrong. And I hope it's now working, because this is all probabilistic. So we can first of all run the unit tests, and yes, also the unit tests would actually fail. Okay. And maybe some of you know we have been working on delta debugging of this thing. So we can reduce this with a cadical. And then we get a small CNF out of it. Okay, sorry, this was not right, because I checked proofs. That's probably the, yeah, that's not working this way. So I need to compare it. So this is not working this way, but because I need to do proofs. But a much better way of checking this is running the Mobicle solver. And then you see what's going to happen. It will generate again random traces. So I press Control S for stopping it for a second. Like for instance, the 8 random seed, which was this one here. This actually led to a bug, and we'll see the bug in a second. So if you take, for instance, this trace here, or let's pick this one because it has a very small result, and we're running this trace. So maybe you want to see the trace first. So this is the random trace generated, right? And a big trick here is to also randomly generate configuration options of the solver. Then yeah, there's like one solve, there's another solve, and then there's like, because it's unsat, it would ask for failed literals. Okay, now if you replay this trace, you saw already what happened, right? So the solver is run, and then the internal proof checker actually fails. Okay, so Categorical has internally a proof checker which online checks whether the proofs the clauses learned are actually implied by the formula, and that proof checker fails. And this proof checker is also like non-deterministically by the enabled or disabled. And now what really happens is this Mobicle also is a data debugger, and if I run the input here and I want to keep the bug but want to make the input as small as possible, then it would do that. And by sort of removing clauses, so it's also like a grammar-aware data debugger. And then you have a really small trace, like this one, okay, and this really triggers the same bug, which is quite impressive, I think, right? And now you can go on and debug this. The first thing I would do is I would configure Categorical with debugging information, and then also say, please, oops, I need to say with logging. And then run the thing with the -L. Yep, and then during this minimization here, probably the last one, there was one literal removed, and that was probably due to this buggy version of the code. Okay, so this is extremely useful if you want to hack Categorical, because you will be able to get like you have all this testing set up, and you can run it. So one thing more, if you run this without options, right, then it will just run forever. And that's extremely useful, as you can see, and that's like what I usually do, because some of these generated traces, like this one, is very small, and then of course you want to look at those small ones first, right? And that was due to that bug here. All right. The other thing I wanted to show you maybe with the code is some things which are really complicated, is how the clause data structure is done. And this is also like mainly one of the main differences between Categorical and KISAT. And you see already here, this is not trivial and complex, but I try to make everything documented. So if you find something which is completely unclear, let me know, and I'll add this. This is like my goal, and it's of course the idea with this Categorical is that you're it serves as a purpose of documenting sort of like my insights, but also maybe of the community, and also help people to hack SAT solvers without sort of like like being lost in all these different papers and whatever. Okay, now I could, of course, spend days on this, on the code of Catechol, but I want to say something briefly about KeySAT. So we have the same thing here. So this solver here um, is kind of a port of Catechol back to C because of this issue with the memory. I showed you this tweet, right? Where people were doing using these solvers on very large things, and they get it out of memory. So like I have a collaborator in industry who was going with me through Catechol and trying to figure out whether also int max variable, that's 2 billion variables, would be possible with Catechol, because they obviously have cases for that, which I find really unbelievable, because you really need a terabyte main memory machine to just run this. And then I started to rethink how to organize the clauses, and that's way more complicated here in the in KeySAT. And unfortunately, but this is kind of because it's like the first try. There's nothing documented. So here's like a similar data structure for KeySAT, and the most complicated thing is actually here in watches, and because binary clauses are not kept in an arena like other clauses. They just don't exist really. So they only exist in the occurrence lists. And then you see all this bit stuffing. Then you need to do some issue with big endian and small endian. So that to sort of easily fit this whole thing into 32-bit. And the downside of it is that the maximum number of variables is 2 to the power 28, which is 256 million variables. So if you want to have, so it's twice as many as Linkeling. So like this one test case by this tweet would not fail with KeySAT, but I don't know how to get one more bit out here. So actually, this is currently sort of what you can do by sort of focusing on making it compact. And unfortunately, I think if you really want to remove this limit, you really need to double the memory footprint of the solver. And that's something which in practice, of course, is a problem if your instance is already running into sort of like a 128 gigabyte machine and then hits this limit. Now, if you want to use another solver, you would need already from the very beginning a 512 or maybe even a terabyte machine. All right, so I think this is what I wanted to show. So KeySAT is not so what one of my postdocs is actually doing, he's working on KeySAT too. He is looking at Catechol to understand what's going on in KeySAT, but there are a couple of algorithmic differences which of course exist and which are not documented at this point. Yeah, the testing at KeySAT, as you can see, is parallel, so it can actually run. It can make use of these 8 core machines quite nicely. So it would really take, if you take one processor, I think it's like way slower. No, this was not P, a T1, I think. No, I forgot the, not, okay, sorry. It's called TSAT. No, not P, it was a T. Sorry, I forget my own. J, of course. Then it will only run one process, and it will take not much longer, of course. But as you can see, these are all unit tests. So these guys are like hard-coded C unit tests, except for this one, which would use read CNFs. So KeySAT is not incremental yet. It has only a subset of the API functions which are here in this file. But this will change hopefully in the next half a year. Okay, now we'd be open to questions because, as I said, right, I can go through a specific code, or even like if I would explain everything, it would take days. So please, if there's time, ask questions now. No questions? I think people are still here. No?
Yeah, I think. But
We can also move to Discord if you want, and then stop this part.
yeah, I guess maybe also it's about probably dinner time in India, so
Yes.
that may be affecting some people.
Move to Discord. If there are any
Where's my
questions,
window? No.
otherwise we could move to Discord.
I
Okay.
have a question. It's
Yep.
actually general. I tried to use Cadical in my course. Okay, so what I did, I asked student to change the parameters and see the variable, changing the values and the impact on the performance of solvers. So
Yeah, this. Yep.
yeah, so my question is like, is there a justification of these numbers you default to now values you have chosen for several parameters?
No, I mean, like for instance, yeah, what you're talking about, like, so to show to the others, if you do, yeah, then you get only -8, you get a very small test thing. But you do say help, then you get like all these numbers. Now, the reason why they're all not metric constants, but you can change them, is not to optimize the solver for specific applications, but it's for this testing and debugging. Because I think you saw it in this one trace. So it's extremely important if you sort of randomly generate test cases to sort of switch off parts of the code. And that you achieve by randomly sampling these values of the parameter. Okay, and so this you might miss. So there was like a talk also by Karim Sakala once in Vienna Summer of Logic, where he showed the 300 options of Lingeling and said that nobody understands these SAT solvers, but he misunderstood the purpose of these. The purpose is not to optimize this, to use these parameters for optimizing the solver to a specific application. No, it's like for usually, actually, if you change the parameters, it gets worse. But to sort of enable more the rough testing and in particular delta debugging. Okay. But then some of these parameters are documented. So where's my decay? Oops. Score. Yeah, score. Here's the score factor. This is 0.95, which I had on the slide before, right? This is just sort of this F you saw before. But of course, and 500, right? 500 per mil would be sort of 0.5. And that would be like 95%. This is like for the exponential visits, the parameter. Of course, like you need to know quite a bit about SAT solvers already to figure out that this thing here is actually determines the decay factor. Yeah, here, for instance, is an instance. This is implemented. It shuffles the variables similar to, but it's completely useless. But I kept the code in it because it helps to debug and test things. Also, like block is of course false, as I explained before. It turns out to be mostly useful, even though I think useless, because I even think this version implemented in Catechol is the fastest version probably existing. Here you could completely switch off bumping and things like that. but there's not more. Yeah, so here, this thing here, this is from the paper from the two friends from Intel. They put 100 here. And of course, you need to make this connection. But if you, for instance, Google for that thing, grab for that thing in the code, then you will see this is in analyze. Okay, and then let's grab for that. And then it should here somewhere say that this is related to this paper. And then you, of course, need to find that paper somewhere, I should say. Sorry about that. Now, this is the other one. Yeah, chronological backtracking. So you would need to find the paper where this is implemented. Yeah, I don't think there's like this is very hard, right? So it would be really nice to have this all sort of clickable, and then you would get the paper or some connection, but I don't know.
Yeah. So, I mean, this I read through this output of this your help, and then chose some parameters which I did not fully understand, and asked students to just play with them and see. I mean, it didn't, as you said, the default values mostly work best, and others just really didn't work or didn't change anything. Okay.
Yep.
Yeah, so but it would be nice that you have like some way of, like you pointed out few parameters which are interesting, to know that, yeah, you can play with them, and then you can see
Yeah, so now
some
there's
performance
like,
change, something to observe.
yeah, like two parameters which are kind of more meta parameters. So these low level parameters, I don't show them on purpose, not configured. Sorry about that.
Okay.
Um, and these are at the beginning, so like before the list of low level parameters, and these are these two are kind of interesting, okay, but in particular, if you want to use the solver as a preprocessor, so you can use Catechol as just preprocessing a formula, and with this capital P, you're giving the initial number of preprocessing rounds, and then this guy here just sort of in optimization level 1, it would or 1, 2, 3, 4, 5, it would increase certain limits by 2 to the power of this number here, so exponentially, right? Like one which have very high upper limits would have 10 to the power of that. And with that, and in combination of these two, you would really get more preprocessing effort. However, the scheduling, which we didn't have time to talk about, is now, I would say, almost is in a very good shape. Because KeySAT is even better. That usually you don't gain anything with that, because in many, at least on average, for these instances, it's better really to rely on this default sort of like preemptive search, and then a little bit of preprocessing, not that much. And this not that much would be sort of changed by putting here a 2. And there's only very rarely that this helps. Okay. Similar to that, you could just put here, like, do the preprocessing up front. Usually it waits for some time. And that's also very rarely, like I would say like 5% of the cases. But if you want to plan, if you plan, for instance, to run this on say competition benchmarks or diverse set of benchmarks, these will not help. Only if you have some very restricted set of instances. And the thing which helps is these, I call it not options, I call them configurations. And I think you saw them. So these are kind of things where I look at the results of Catechol on satisfiable instances and on unsatisfiable instances, and I change like some options, in particular these target phases and how often you restart, and whether you only do stable or non-stable mode, and then pick those specifically to sort of like have higher chance on satisfiable instances, and that's useful, right? And Yeah, but it's only a very small set. It's
Mhm.
implemented here in the config CPP. So you see here what's happening. So the SAT for SAT, you get these three options. You could also just do them manually. And for unsat, I have these two options. And I try to increase it, but it's not useful. So this is kind of the local sort of thing I found, right? And of course, if you would have other benchmarks, you could try also like some of these, and you could put in a configuration, like configuration which says, I don't know, like favorite benchmarks X, and then, yeah.
I have a question.
Yes.
So let's suppose if we gave a general SAT problem to
Yes.
Cadillac, and what is the where does the Cadillac spend most of its time? So what is the intensive part in that? So is
Well,
it
most
the
most of its time, it's really search in propagation. So maybe I'll just show you like maybe one of the latest runs I have on the cluster. So I'm just working on KeySat for this all UIP thing. And if I take the sorry, I need to go to the cluster. And now KeySat's 2020, and maybe latest one. Yeah, this is the one version which was kind of in the competition, but with profiling information showing. And now if I go here for search, and in these log files, I get this profiling. This is time and percentage spent in search. If I now assert this, for instance, this was your questions, and I regularly do this. With this one, you see, yeah, some of them actually, like this one is bad, so I would need to check this out. Why is it like spending 89%? No, sorry, this is search. Yeah, this is good, right? So I want to
yeah.
say the opposite. I want to do reverse. Yeah, here's one where it's the opposite. Search is only 9%, 15%, 23, right? Yeah, but you see, there are not many instances where search is not used, and also like the absolute time is not high, right? So here we already at 50%, right? 50% of the time is search, and this is like from 400 benchmarks, right? And these are all which have far less time spent in pre-processing. And then if you go to search, you will realize that it's really in the propagation. Propagation is the hotspot. It's like, I would say,
any specific data structures for the propagation so that you can
yes. So I can even, yeah. Maybe because we're at it, I can even point you to the point in the code, which is the hot spot. Cadical source. And it's, I think I even say this here. So it's this, yeah, here it says, this is the hotspot. And unfortunately, this is something already complicated why you need this garbage thing, but like, let's not go into this. If you're a little bit more careful, you won't need this garbage thing. So where are we here? So this is the propagate function. So the propagate function goes over the trail, right? Like the not yet propagated variables on the trail gets the literal, right? And it propagates it. Then it gets it watches, and then it goes over these watches. So this is this loop. Now it goes over the watches of this. Okay, and then we have this binary thing. Like for binary clauses, we don't need to access the clause data because like it's inlined in the occurrence list. But there's something here which you can read, and which Matthias, my now postdoc, figured out while he was not postdoc yet. And because I also had this line here, and that's bad because then you need to go to the clause, which is a pointer dereference. Here, everything is in the cache. You don't need a pointer dereference. And yeah, it's complicated. So you can check how did I get rid of this line, right? Which was really slowing down the solver. But now I'm here in the sort of big clauses, which are not inlined. And now I'm accessing the clause. So this pointer dereference here, Knus calls it the mem, right? This thing here. This is the hotspot because it's the first time you access that sort of randomly selected clause in memory. If you would not have this issue with this garbage, which I cannot explain now, it would be the next thing when you accept the literals, because this pointer here, okay, the accessing this pointer is still local. You have this in a cache line, but now you need to read the first literal. And then this would be the hotspot here, like accessing this first literal and also the second one. Then you would argue, why is there this complicated XOR? Well, it's to make this code here branchless because in the Minisat, this is done with a branch. But this really also slows down the solver by, say, sort of 5%, because it's the absolute hotspot of the solver. That's why we use this strange XOR trick. And I explain it here why, right? So this is kind of the thing. All right, and then, so you see, if there would not be this issue with this checking this garbage flag, which you need to avoid, propagating garbage clauses for strange reasonings, can read up on that. This would be the hotspot, accessing literal of the clause in propagation. And that's why you don't want to have a branch here in this one.
Yeah.
In KeySat, I got rid of this thing. So there's really the hotspot. So I can show you the hotspot on KeySat if you want. Yeah. So it's the same thing. It's like, here's the hotspot. Here's real. Oh no, here's also the C garbage. Yeah, sorry, I still have that. It's the hotspot is here.
Mm-hmm. So
and you can really, and I think it's really 80% of the time. So if you would only run search, it's 80% of the time. And that's really amazing. And then all this other code here down here is complex and whatever, but it's not taking time.
Like 80-20 rule, isn't it? But so I have one more question. So it seems like it's a big software, you have a lot of functionality, but adding functionality makes the software complex. And doesn't
Yes.
it slow down? So what is the trade-off like?
Yeah, this is exactly the point. So this has been a struggle for years. That's also why I implemented, I think, like number 10 SAT solver, because like whenever you learn something, you think, okay, now I can simplify it, right? But it's true. You see, there's like always like this compaction thing, but then people come up with new ideas, and putting that in is really complicated. So for instance, one thing I really hate is the sorting, right? So it turns out that for this VMTF, it's better to bump the literals in the order of their stamps. And it's very simple, like it's very compact code. You can use the standard sorting algorithms from the STL, but it turns out that for very few benchmarks, like for 10%, suddenly this sorting becomes almost the biggest hotspot after propagation. Okay, and because of that, I had to implement my own radix sort. It's called, how is it called? I forgot. R something. Oh, yeah, in KeySat, sorry about that. Yeah, in KeySat it's the same, but so there's like so it explains why, right? And it's really awkward. So I had to implement my own radix sort. It's this header file, right? Which of course it takes a day to get this right, and you need to find the right parameter. But you win then on these very few benchmarks 30%, and it's of course only a switch, right? So it's not sort of runtime, but it gives you like for few benchmarks like 30% running time, and these are the things which I don't like. But of course you want to have that in the SAT solver, right? You don't want to waste on these things if they're in there. And there are lots of other things like that, sort of where you yeah, for simplicity and for explaining the thing, you're going to you don't want to do it, but for getting a state-of-the-art solver and using this thing in real life, you want to have that complexity. But it also brings us back to the type of research you want to do. So the problem is if for instance, like one of you is working on a paper for changing something in the SAT solver, then it's very hard to argue that your change is useful if you don't compare it like against the state-of-the-art solver, right?
Yeah.
And that's sort of a problem with how we do science, I would say. And if you would know how to do this differently, then yes, there should be also a solver which only has sort of the sort of least number of features and the least complexity of the code. But until it's not the case, I don't know. And even then, you see, if you would have that, you would still need to port these insights back to sort of like the most competing solvers. So it's a difficult situation.
Yeah, just a comment here. So in my master's research, we were working with the counting and queens problem with
Mhm.
Oliver, and we found that simply using DPLL without any additional functionality, that was the best we could get.
Yes.
Even in the state of the art, that was the best. So
Yes.
that means there are some problems where just having the plain old DPLL or a simple implementation is quite
Yes.
better
Yes. Yeah.
than
True.
one more question. So you use some optimization flags in compilation, right? So did you
One
try with
is
the
it
G++ when you are compiling the software? You were using some compilation flag
Yeah.
optimization flags.
Mhm.
So did you play around with it, or are they standard?
Oh
Are
yes,
you
so of course, like I've been following this for also like 30 years now. So
yeah,
this is of course in constant sort of learning curve. Now at the point, for instance, this is also like happened like 3 years ago when I started Catico. I still used my own stack implementation because before 2017, um, I was always faster with that one than the standard, well, than what current C++ compilers would do. But this
yeah,
changed, right? So and of course, like I was using that back then compilers which were already 3, 4 years old. So I would say this probably changed like 5 years ago. And the reason for that, so I really dig down to it, so really to the assembler and everything, is because they have specific allocators for vector in C++. So they know that most people use vectors for so many things,
mhm,
and they have specific C++ allocators with arenas just for these vectors. And and this beats my basic sort of simplistic homebrew allocator, because they spend so much time on that, on have a really sophisticated sort of allocator just for this purpose. Okay, and that's why I removed this. And yeah, there were benchmarks where this costed me 20%. I'm not joking, right? And this was a kind of surprising. However, then when discussing these big memory issues with Cadigo, I figured out that C++ has another issue, and I'm not sure they can fix it. It's like when you allocate a vector, it really needs to initialize all the elements. Like if you say you put a vector, for instance, of decision levels, and you have like 1 billion of these, the C++ semantics will force you to initialize every single value of this vector. While if you use C, you can use calloc, for instance, which is a system which goes to the operating system, gets you 0 pages, which are only initialized on demand when you really access that pointer. And already that gives like a tremendous speed up in initialization for KiSAT. So KiSAT is like way faster in sort of like ramping up. And in addition, um, doesn't need that memory. So and I don't know how to fix that. Okay, so in C++, so I tried like various ways, and the one way in Caticle was to sort of again take all the memory management into my hands, but yes, so I'm saying this is a constant struggle. So we don't know how this will be in 5 years, when maybe compilers will, for instance, figure out that you're doing here a stack allocation, and there's an int in it, and this int is always 0 initialized, so better just use calloc, right? But it's currently they can't.
thank you.
it's so um, I guess we can move to Discord. Thanks a lot, Armin, for really marathon 5-hour tutorial.
Or is it 5 hours? So sorry about taking that.
That's a lot of stamina and work. So I think there are still quite a few people probably would interest to talk to you over Discord. So if you have some time, that would be really
Yes.
great.
Let's meet in Discord.
Yeah. Thanks, everyone. So we'll start again tomorrow at 1 p.m. Indian time. Sorry, 10:30 Indian time. I converted it to Singaporean time. So 10:30 a.m. tomorrow morning with session. So hope to see all of you tomorrow. And now we are going to move to Discord. Thanks a lot, Armin, for virtually joining us. Hopefully you'll also come to India